We have identified the stacking of base pairs in close contact with one another through the core of the double helix as a possible major term stabilizing the structure. But what we've already emphasized is that the folding of DNA into this double helical arrangement is an equilibrium between the folded state and an unfolded state in which the strands separate and lose much of the structure that they had when they were twisted together. And if you're going to understand an equilibrium, you have to think about both sides of it. In other words, in effect, what we're asking is, why is this equilibrium shifted over towards the left to favour the double helical structure? And we can only answer that properly by thinking about the interactions in the unfolded state as well as in the folded state. So when we were talking about hydrogen bonding, we emphasised that groups which hydrogen bond to each other within the double helix then hydrogen bond instead to water when the double helix unfolds. And the same kind of thing is going to be true for all these other interactions, that where the bases are stacked up on top of one another in the folded state, those exposed faces when the helix unfolds will then be surrounded by water molecules. So in order to go further with this, we need to think a lot more about what water is like and about what the consequences are going to be when it's exposed to the various groups in the DNA, but in particular those surfaces of the bases. So let's start by looking at ice. So here is a model of the crystal structure of ice. So the individual water molecules, remember, red is the oxygen, white are the two hydrogens, and you can see it's an extremely regular structure. If we rotate it round, you can see the water molecules are effectively arranged in layers like that, and that within each layer you get this sort of hexagonal arrangement. Now, as you would expect, the structure is held together primarily by hydrogen bonds because those are the strongest intermolecular forces available between the molecules. And if we show the hydrogen bonds, you can see there's a whole network of them both between the layers and within the layers like that. If we switch to a space-filling representation like this, you can see that optimizing the hydrogen bonding, which is what the structure does, has this interesting effect that it leaves great big holes in the structure, which you can see here. And again, if we rotate it round, you can see there's a whole network of cavities in the structure. And that gives ice a lower density than you might expect for a solid, and of course that's one of its famous properties. If we switch now and look at an individual layer, we can see more clearly the details of the hydrogen bonding of each water molecule. So each hydrogen, you can see, is forming one hydrogen bond. And notice the linearity which we talked about before when we were discussing hydrogen bonding. So you have OHO in a straight line here and again there. So that's two hydrogen bonds per molecule formed by the hydrogens. But in addition, the same molecule is forming two further hydrogen bonds to the oxygen, and those are pointing in the directions of the lone pairs on the oxygen. So it's got really idealized hydrogen bonding with 4 hydrogen bonds for every molecule in the lattice structure, except obviously at the surface. So let's have a look now at what happens when the ice melts to form liquid water. So here's a fragment of ice again with the hexagonal structure, and we'll just look at what happens when we put some energy in and start it to melt. You can see lots of vibration within the structure, but at the edges you can see the hexagons are breaking down, and eventually the whole ice structure is broken down. But what you can see is that the molecules haven't spread out. If we zoom in a bit like this, you can see that the water molecules are still forming lots of hydrogen bonds, they're still clinging closely together, but they've lost that regularity of structure. We can get a bit more of a detailed view of what's going on with the molecules in liquid water if we look at a more detailed molecular dynamics simulation. So let's start first of all just with this snapshot. And if we focus on this particular molecule, which is sort of approximately center screen at the moment, you can see that it's forming the classic 4 hydrogen bonds, just as it would do if it were in an ice structure. So you've got the hydrogen bonds are shown by the purple dotted lines here, and you can see you've got the 2 hydrogen bonds from the oxygen, and then one from this hydrogen coming up here, and one from that hydrogen going down there. But you can also see that the water molecules surrounding it look pretty randomly distributed. There's no regularity like we saw in the ice structure. Now let's look at what's actually happening if we set this in motion. So you can see there's a lot of localized motion of the water molecules. They're not sitting still in the structure. You can see that they're vibrating, so the lengths of the bonds are changing slightly with time. They're also rotating around, so that the angle of this relative to you is changing. And over time you'll also see that there's some translational motion, so you get new molecules drifting into shot as time passes, showing, so there's one creeping in up here which wasn't there before, and that shows you that there's translational motion, that the average position of the molecules is changing over time. And it's important to get a feeling that what we're looking at here is massively slowed down. What we've looked at so far is actually about 0.7 picoseconds. In other words, 0.7 times a millionth of a second. Is what we're looking at here. So we're talking about really fast motions here within liquid water. But the other thing to focus on is that you can see that although the molecules are forming the classic 4 hydrogen bonds for large proportions of the time, they're not doing it all of the time. If we just scroll this back to where we were at the beginning, this was the one we were looking at, forming its 4 hydrogen bonds here. But you can see every once in a while one of these hydrogen bonds breaks. So this one's just come back again, but as it moves around, that one goes again, and then that one goes again, and so on. And so what makes this mobility possible in liquid water is the fact that on average each water molecule is not making 4 hydrogen bonds. On a time average it's making 3 and a bit hydrogen bonds. Depends on the temperature, and people disagree about the exact number, but if you think in terms of an average of around maybe 3.5 hydrogen bonds per molecule, that's what you have in liquid water compared with 4 in ice. Remember that every time a bond is formed, any kind of bond, including hydrogen bonds, which is what we're mainly concerned with here, every time a bond is formed, energy is released. And that means that the system containing those bonds moves to a state of lower energy because the energy's been lost as heat. And because ice contains more hydrogen bonds than water, remember 4 hydrogen bonds per molecule here, 3.5 or so in liquid water. More hydrogen bonds means more energy has been released, which means that the ground state energy, the lowest possible energy in ice, is lower than it is in liquid water. So this difference in energy here reflects the difference in hydrogen bonding. So what does that mean? Well, what it means is that at extremely low temperatures, if we were close to absolute zero, where there is very little energy available to put into the system, it would definitely be ice, because all of the molecules would essentially be trapped down in this lowest level here. But then what happens as we start to warm things up is that more energy becomes available, and that allows the system to start to populate higher energy levels as well. So we get a Boltzmann distribution of energies where not all of the system is in this state, but some of the molecules move into higher energy states. And in ice, what that largely corresponds to is increased levels of vibration, because although the structure remains intact, the molecules can vibrate around, and that's what's happening as it gains energy here. But at low temperatures there really still isn't enough to start populating water, because you've got to reach this threshold energy before you can break this structure down. However, once you reach a high enough temperature where basically these energy levels become accessible, then the system has a choice. Because if you're going to populate levels up here, you could either populate them in ice or in water. And what you can see is that there are many more energy levels available within water. And that's because the water molecules, as we saw in the simulation, are not restricted just to localized vibration. They can still do that, but they can also rotate to some extent. It's not completely free rotation, but we saw them doing it in the simulation. And they can translate. They can actually move from one place to another and change their average position within the liquid. So they have those extra forms of energy, rotational and translational energy. And that means many, many more energy levels. And we talked before about this idea of entropy, that the universe works in a way that energy always tends to populate a bigger range of energy levels if they're accessible. It will always tend to spread out rather than focus in a particular state. And so what will happen is, once there's enough energy around the population of these levels, or these levels becomes possible, it will favor these ones, just because that then disperses the energy more widely. And so what happens is, eventually, as you raise the temperature, the ice melts and water is formed because of its higher entropy, its higher dispersal of energy. So why are we talking about all of this when we're really thinking about the structure of DNA? Well, we're talking about it because it's very relevant to that folding equilibrium. So what we're going to do now is think about what happens if a nonpolar molecule dissolves in liquid water. So here is a snapshot of some liquid water. So we've got these water molecules apparently fairly randomly distributed and randomly oriented relative to one another, but actually still forming between 3 and 4 hydrogen bonds per molecule. So it's actually densely packed with hydrogen bonds within this collection of molecules. So here is a nonpolar molecule coming in. So the idea is that this lacks that capacity to form hydrogen bonds. It can form induced dipole-dipole forces, but that's basically all. And the question is, what's going to happen if we bring this and stick it into the middle of this cluster of molecules? So there it is now. It's in the middle of that cluster of water molecules, and they have obviously had to make way for it. In other words, in effect, what we've done is created a cavity in the hydrogen bonded structure. Because as far as those water molecules are concerned, having that nonpolar molecule in the middle there is basically just the same as having an empty space that they're not allowed to go into. So it's like a cavity in the hydrogen bonded network. At the interface between that nonpolar molecule and the water molecules surrounding it, there will be induced dipole-dipole forces. But remember that water structure is dominated by optimizing the hydrogen bonds. So the water molecules won't necessarily be arranged in a way that will maximize that contact surface area between them. And so you could imagine that from the point of view of the nonpolar molecule, this may not be very favorable compared to it being packed against other nonpolar molecules before it dissolved, because it may have less surface contact area with the water than it did with other similar molecules before it was separated out and dissolved. So that's one reason why this may not be favorable. But the big issue is going to be, what difference does it make to the water? If they still keep doing the same thing they were doing before, and reorienting themselves so that they're pointing in different directions as they rotate and translate around, then they're basically going to lose a significant number of hydrogen bonds. Because before the nonpolar molecule dissolved, they would be making hydrogen bonds to molecules within that volume in the middle there a good percentage of the time. Now the nonpolar molecule is there, they can't do that, but if they keep moving with the same degree of freedom they had before, they're therefore going to lose out on the number of hydrogen bonds. So you might expect that dissolving a nonpolar substance in water would involve overall reducing the number of intermolecular forces, because you've had to break hydrogen bonds to make that cavity in the middle into which the nonpolar molecule has gone, and potentially you're also reducing the density of induced dipole-dipole forces compared to what the nonpolar molecule was forming to other nonpolar molecules before it dissolved. So we're going to expect an endothermic process when the nonpolar substance dissolves. So let's have a look at some experimental evidence. So these are data for the solubility of a nonpolar hydrocarbon, 2,2-dimethyl-propane, in water. And what you can see is that at high temperatures, so above about 30 degrees C, delta H is indeed positive, as we predicted, which we could interpret as being due to disruption of the hydrogen bonding in the water. But at lower temperatures, something strange happens, and delta H is actually negative when the hydrocarbon dissolves in water. So something else must be going on here to explain why we get exactly the opposite of what we predicted here. And even here, the enthalpy change is much less suggestive of disruption of lots of hydrogen bonds than you would expect. It's also instructive to look at the entropy change. Now, when you form a solution, so this is a sort of simple picture of going from two separate liquids to a mixed liquid where they've dissolved one in the other, and we've set that up as an equilibrium. What you expect in that situation, and what you commonly get if, for example, you dissolve one nonpolar substance in another, is that you get a positive delta S. And you can see why, because an individual molecule in this state where there are two separate liquids, this state's translational freedom is limited essentially to this small box. Whereas in the solution, it has much greater translational freedom, and more translational freedom equates to more translational energy levels and therefore greater translational entropy as the molecules are able to move around better. So you expect delta S to be positive when a solution is formed. But again, look at the data. These data are actually T delta S. We'll talk about the significance of that in a minute. But T is a positive temperature. So in effect, what this is telling you is that except at very high temperatures, delta S is actually negative when the nonpolar substance dissolves in water. So although this effect must be present, because there unquestionably will be this increase in the volume to which the individual molecules have access, in spite of that, something else must be going on, which means that when a nonpolar substance dissolves in water, for some reason, the energy becomes less dispersed, giving you this negative delta S here. Now, the significance of T delta S is this equation, which is actually one of the most important equations in chemistry, really. We mentioned earlier that when you're trying to decide what's going to happen and what's not going to happen, like is DNA going to fold or not, what governs it ultimately is this balance between sort of two factors. On the one hand, there's the effect of enthalpy, and on the other is the effect of entropy. And we saw that both of these were related overall to the entropy of the universe, that what really governs the favourability of any process is that the entropy of the universe, the dispersal of energy throughout the universe, is always increasing. And any process will only happen, just because of statistics, any process will only happen if it leads to an overall increase in the entropy of the universe. But we saw that that can work in two ways. If you're focusing on an individual system, like a solution of DNA, or in this case, a solution of a hydrocarbon being formed from the separate phases, if you focus just on those phases, there could be an increase in entropy within that system itself, which might make it favourable. But there could be also an effect on the entropy of the wider universe resulting from an enthalpy change, because if heat is released in a reaction, it escapes into the wider universe and increases the entropy out there. So this equation basically combines those two terms, and remarkably it's a very simple way that they can combine like this, that we can define this term called the free energy. And our requirement for entropy of the universe always to increase is embodied in this equation, because what you can show is that only if delta G is negative will a process be really favourable. And that can happen in two ways, either because delta S within the system is positive, in which case you get a negative minus T delta S term contributing to making this negative, or delta H could be negative. You could have an exothermic process releasing heat, increasing the wider entropy outside the system, again tending to make delta G negative, and the combination of those two dictates what's happened. So delta G is called the free energy and is an incredibly important point. So what you can also see in this diagram then is the delta G, and you can see it's positive at all temperatures, although it does change, not surprisingly given this big change in delta H and delta S. So the fact that it's positive means that it's not very favourable to dissolve a hydrocarbon in water, and of course we know that. Oil floats on water, it doesn't dissolve in it. But that doesn't mean it doesn't happen at all, it just means that the equilibrium lies predominantly over to this side. But a little bit of hydrocarbon dissolves in water, even when you have a positive delta G, and therefore you're able to measure these numbers. Okay, so what we have then is a situation where we can explain why oil fails to dissolve in water, in part because delta H is positive, so it's endothermic, and that's unfavourable in terms of the contribution it makes to delta G. But also because delta S, which we expect to be positive for solutions and therefore to be favourable, is in fact negative over most of the likely temperature range. So around physiological temperatures, where we'd be interested for the DNA, you can see that delta H is actually very small, and we expect there to be quite a small enthalpy contribution when a nonpolar substance is exposed to water. But this negative delta S term is going to be the dominant thing, dictating that exposure of nonpolar molecules to water is an unfavourable thing. Now you can begin to understand this slightly strange behaviour in terms of enthalpy and entropy if you look at this molecular dynamics simulation. So what we've got here in the middle is a xenon atom. So this is our nonpolar particle. And surrounding it is a bunch of water molecules. Now this video is slightly confusing. The reason you're getting this rotation is simply that the camera angle is rotating around like this, so the molecules are not really dancing around the xenon like this. That's just for effect. So really they're in more or less static positions. And also, this simulation was actually done with a big box of water molecules all around here, but they've just shown the ones closest to the xenon just for clarity. So, what you can see, and the important point about this, is that the water molecules effectively make a cage around the xenon atom. It's called a clathrate cage. And the molecules immediately forming the boundary layer, you can see, if you look at this one, for example, that it is actually forming between 3 and 4 hydrogen bonds most of the time, just as it would do in normal liquid water. So in other words, the water has managed to avoid massive disruption of its hydrogen bonding, even though it's had to make a cavity for this nonpolar xenon. On the other hand, what you can also see is that the price it's paid for that is that the water loses much of its freedom. So remember, this rotation isn't real. These waters aren't really moving around like this. What's happening here is that these waters have essentially fixed positions, and although they're wobbling around a bit, they're not able to reorient themselves and make hydrogen bonds in completely different directions in the way that we saw them doing in the simulation of liquid water. So this layer of water immediately surrounding the nonpolar group is actually behaving more like a layer of ice, where the molecules have some ability to move in a sort of vibrational way, but they can't rotate around and form completely different hydrogen bonds 1 femtosecond than they were a femtosecond before, and they can't translate to different positions in the way we saw them doing in bulk water. So what does that mean in thermodynamic terms? Well, it means that the enthalpy change of forming this cavity to accommodate the xenon is very small, because we're still forming the same number of hydrogen bonds roughly as we did before. But there is going to be an unfavourable entropy change because the water molecules have lost some of their freedom of movement, so they have fewer energy levels over which the energy can be dispersed, and therefore they are in a lower entropy state, which of course is exactly what we saw from the evidence from the enthalpy change of solution of 2,2-dimethyl propane. So this is called the hydrophobic effect. Hydrophobic means water hating, and it's the sort of general picture of what happens when non-polar molecules dissolve in water or are exposed to water. That it's unfavourable in free energy terms. But exactly why that is depends on the temperature. However, around room temperature or physiological temperature, predominantly it's an entropy effect, because the water rearranges itself to compensate for making the cavity, and therefore the change in the number of hydrogen bonds formed is small. But it comes at this price of having lower entropy than you would expect in bulk liquid water. So when we come to apply these ideas to DNA, of course we're not talking about solubility now, because the DNA is in solution in water anyway, regardless of whether it's folded into a double helix or whether it's unfolded. But the hydrophobic effect is very relevant because the exposure of non-polar surface to water is very different. In the unfolded state, those bases, the rings with their big, flat, largely non-polar surfaces, they're going to be exposed to the water. And so we're going to get an unfavourable entropy associated with the water around these rings having to become quite organised in order to avoid paying a price in terms of the number of hydrogen bonds per molecule. When the DNA folds up into a double helix, those bases pair up, but more importantly, from our point of view, they stack on top of one another, and therefore the exposure of that flat surface to the water is massively decreased. And so those bits that are stacked together, the water no longer has any contact with, and that releases the water molecules that would have been doing that into the bulk water, where they have much greater freedom to form hydrogen bonds, but while still being able to move around. And so formation of the double helix is going to have a favourable entropy contribution, which comes from release of ordered water solvating the flat surfaces, becoming more disordered water in the bulk solution. Now at higher temperatures, remember the hydrophobic effect is different. At higher temperatures, the water surrounding nonpolar groups is less inclined to form this kind of ice-like ordered layer around it. And instead, it pays the price of forming fewer hydrogen bonds per molecule in order to retain a higher degree of mobility and therefore a higher entropy. So we can look for evidence of the hydrophobic effect playing a significant role in folding by looking for that characteristic temperature dependence. So removal of these non-polar surfaces from exposure to water is expected to be favourable. In other words, to make a favourable contribution to the folding of the double helix at all temperatures. But the thermodynamic detail of what drives that is expected to be different. At lowish temperatures, including around physiological temperature, it's expected to be primarily an entropy effect. That taking that non-polar surface away from the water allows the water more freedom of movement and therefore makes a favourable entropy contribution. At higher temperature, we expect the water to sort of refuse to pay that entropy price, and instead the removal of the non-polar surface from the water at high temperature is driven primarily by the fact that it allows the water to form more hydrogen bonds when they're in the bulk phase than when they're surrounding the rings here. So we can look to see if there's evidence of that in the actual thermodynamics of folding of the DNA. So here are some experimental data. So what this is showing you is the enthalpy change per base pair for unfolding of the DNA. In other words, for going from the double helix to the more disordered, separated strands. And you can see that it's a positive delta H. But that what's particularly relevant in terms of what we're talking about at the moment is that that delta H becomes a lot more positive at high temperatures around 80-90 degrees than it is at lower temperatures. And that's the signature of the hydrophobic effect. That at high temperature, exposure of non-polar surface to water elicits a price in terms of the water making fewer hydrogen bonds, and therefore there being an enthalpy price to pay. At lower temperatures, it doesn't pay that same enthalpy price, but there is an entropy price to be paid. But it gives you that characteristic increase in the positive delta H as the temperature goes up. So that strongly supports the idea that the hydrophobic effect is important in driving the folding of DNA. So here are some data then which tell us not just about delta H this time, but also about delta S and delta G. Delta G, remember, is the free energy change, which is defined by this equation. And that's the thing which overall determines the favourability of a process. And what they've done here is they've broken down the contributions to these three terms for CG base pairs and for AT base pairs. So if we look first of all at delta G, which is the overall favourability, you can see delta G is positive for unfolding. And that's telling you that under these conditions at 25 degrees C, the double helix is stable, because unfolding would be an unfavourable thing. What you can also see is that the contribution to delta G is bigger for GC base pairs than it is for AT base pairs. And we've already mentioned that it's been known for a long time that DNA with a higher content of GC base pairs has a higher temperature required for its unfolding. In other words, is more stable. And that's supported, therefore, by these delta G measurements here. When we look at the delta H and delta S, you can see that delta S is positive for unfolding. In other words, the dispersal of energy is greater when the DNA is unfolded than it is when it's folded. And that's something we talked about right at the beginning. You know that's going to be the case because of the massive increase in the independent mobility, first of all, of the two strands from one another, but also of the ability of individual bonds within those strands to rotate. So there's many more accessible energy levels in unfolded DNA than there would be in the folded DNA, and that's why the entropy is positive as we would expect. But it's less positive than it would be in the absence of the hydrophobic effect. So yes, unfolding is favourable in entropy terms, but it's much less favourable than you would expect if you ignore the entropy of the water, which is better off when the DNA is folded. But what these data also tell us is that the hydrophobic effect alone is not enough to make the double helix stable, because delta S is still positive for unfolding, which means that if it were down to entropy alone, unfolding would be the favourable thing. That's what would happen. What prevents it from unfolding is that in addition to the hydrophobic effect, you have something which makes delta H of unfolding positive. And remember, that's unfavourable. That's going to tend to keep it in the folded state. And that brings us back to the stacking interactions that we talked about, that the increased density of intermolecular forces between the bases and their surroundings when they stack on top of one another makes for a favourable contribution to the stability of the folded state. And notice that we're saying that this delta H comes from the stacking interactions, not from the hydrogen bonding. And we talked about the fact that we expect the contribution to delta H from the hydrogen bonding to be small, because basically you're just replacing one set of hydrogen bonds with another. And there's actually some interesting evidence for that here, which is that if you compare GC with AT base pairs, remember when you break a GC base pair you're breaking 3 hydrogen bonds. When you break an AT base pair you're only breaking 2. So if the hydrogen bonding enthalpy were a significant factor, you would expect to have a more positive delta H for the GC base pair, and you don't. And of course the reason for that is that yes, you're breaking 3 hydrogen bonds, but you're replacing them with hydrogen bonds to water. So it's all sort of fairly enthalpy neutral from the hydrogen bonding point of view. So the reason that GC base pairs make a bigger contribution to stability turns out to be an entropy reason, as you can see here. So there must be something, meaning that unfolding is less favourable from an entropy point of view when you have GC base pairs being released than when you have AT base pairs being released by the unfolding process. And that's quite interesting. So we've talked quite a lot now about the entropy of the water and how it's affected by the burial of hydrophobic surface as a result of forming that stacked core of bases in the structure. So that's a favourable effect that helps to drive the folding of the helix. But there is another aspect of the water entropy which is actually going to work in the opposite direction. And we can get a clue about that if we just look at the water molecules which are detected actually in the crystal structure. So you can see that there are actually a lot of water molecules which show up as having essentially fixed positions as shown by the crystal structure. Because if they were moving around, they would be in different positions in different molecules, and they wouldn't therefore show up as well-focused density, electron density in the crystal structure. So what this result is telling us is that there is actually quite a lot of ordering of water around the molecule. This picture comes actually from a molecular dynamics simulation, which is a way of trying to get around the fact that you don't have any evidence about the mobile waters actually in the crystal structure. But in the dynamic simulation, you allow all the waters to be present, and you still find that you get this set of waters with a long residence time, in other words, which stay in fairly fixed positions for long periods of time. And you can see slightly different behaviour in the two grooves here. So these light blue ones here are the waters in the major groove, and you can see there are quite a lot of them, but they're fairly kind of scattered around. There's no really very fixed structure in the major groove. But in the minor groove, which is here, you get this spine of waters forming a continuous hydrogen bonded network all the way around the minor groove. So what's happening here is that, as you can see there, the water molecules are hydrogen bonding to each other, but they're also hydrogen bonding to bases within the minor groove, and of course they're also hydrogen bonding to the wider water molecules outside. So these fixed waters, and in particular this very fixed structure in the minor groove, are going to be reducing the disorder of the water, and therefore reducing the dispersal of energy, because those water molecules will have limited freedom of movement, and that's making an unfavourable contribution towards the stability of the structure. If we look again at the hydrogen bonding of the individual base pairs, you can see what the availability of groups is for forming these hydrogen bonds to water in the two grooves. So for a GC base pair, you have 3 hydrogen bonding groups pointing into the major groove with availability to hydrogen bond to water. So you've got the NH2, which is forming one of the Watson-Crick base pair hydrogen bonds, but also has the other hydrogen available to bond to water. Carbonyl has one of its lone pairs, and the nitrogen has its lone pair. So 3 hydrogen bonds to water on the major groove side, and another 3 on the minor groove side. If we look at an AT base pair, again it has 3 hydrogen bonding groups on the major groove side, but it only has 2 on the minor groove side. And that could be a reason why the water could be more ordered around AT base pairs than it is around GC base pairs, because the more availability of hydrogen bonding you've got, potentially the more different ways water molecules could arrange themselves around it and still form, 3 to 4 hydrogen bonds per molecule. If you only have these 2, as you have with an AT base pair, it probably restricts the mobility of the water more. And that's certainly not a hard and fast explanation, but it's a possible reason for our observation that when you put an AT base pair into the double helix, it seems to have a less favourable entropy contribution than when you put a GC base pair in. So you can see the water is just incredibly important in terms of understanding the stability of the double helix. And that includes the hydrophobic effect, but it also includes the solvation of the hydrogen bonded groups.